Good evening, this is George Nogic. Today is Sunday, August 5th, and in this video I'm going to solve a problem in electrostatics. I'm going to determine the capacitance between two spheres of unequal diameter. Some people have asked me where I came up with the formula for the capacitance between two spheres. They couldn't find the equation on the internet, and the truth of the matter is I computed it because I had the same problem when I looked around for the capacitance between two spheres that I was using in my dominant force video, the dominant force in the universe. I found various formula out there, but none of them looked right to me, and when I looked at limiting values, they were wrong. When say the spheres got close to one another where they're touching, or you put in equal diameters for the two spheres, the equations were not correct. And I was rather surprised by this because I found these formula at the University of Virginia and Stanford University and various electrostatics lectures and their exam problems, and they weren't correct. And that puzzled me because it's not that difficult of a problem to solve. And I will show you how I solved it. Now, the capacitance between two conductors is defined to be the ratio of a charge on any one of the conductors to the voltage between the two conductors. Whenever you have two conductors, two conducting structures, it doesn't matter what the geometry, let's just say pick a complicated geometry here and another geometry here. These are two conductors. Say I place a charge Q on this conductor, an equal but opposite charge on the other conductor. There'll be an electric field set up between them. The field will be rather complicated. You'll have field of various, the electric field will be kind of complicated. And the trick in solving the capacitance between a structure is to know what the electric field is. You have to get a mathematical expression for the electric field between the two conductors. And once you have that, then you can determine the voltage between the two conductors. Or if you knew the voltage between the conductors, the potential field, you could get the electric field by taking the gradient of the voltage minus the gradient of the voltage. That would give you the electric field, and then you could compute it that way. But standard way of doing this is you assume you place a charge on one of the conductors, and by hook or crook you try to determine the electric field between them and then find the voltage. Well, the way you find the voltage is the voltage between two conductors is just minus the integral of the electric field between them from the point of lower potential to the point of higher potential. That is, you integrate going against the electric field. I'll show you why that is in a moment. And then you compute the charge on the, or from the charge on the conductor, you can get the D field, because the D field is a closed line integral. This is Gauss's law of the D field over a closed volume. And from the D field, we know that the D field is epsilon E. So knowing the charge, you can put a little pillbox there, get what the D field is near the surface, and the D field, the magnitude of the D field is the surface charge density. That is charge per unit area on the surface. And from the D field, once we have the D field, we can compute the electric field just by dividing the D field by epsilon, the permittivity in the medium between the two conductors. Now, so with this, this is the way you would do it in general. And you need to know the mathematical expression of the electric field in the space between the two conductors. That's the problem. That's the crux of the problem in solving for the capacitance for any particular geometry. Well, we know a sphere has perfect symmetry. That is, it looks the same from any direction. And let's assume we have two spheres. We have a larger sphere of radius b, and we have a smaller sphere of radius a, and they're separated by a distance d from their center to center spacing. And what we want to do is figure out the electric field between them. Well, we don't know in general how the field, we can plot out, sketch it out, because we know the field lines have to leave one surface orthogonally or perpendicular to the surface and come to the other surface perpendicular. So we can get an idea of the field lines. The field line here would come straight down, around, and then back up to here. There'd be a field line coming out all the way around and coming in orthogonally or normal to the surface. Well, we can compute the equation for one of the field lines, and that is the field line that goes from center to center. We know that given a sphere that has a charge of plus q on it, by Gauss's law, the magnitude of the field at some point, radius cap r out from the center of that sphere of charge, is q over 4 pi epsilon r squared, the distance from the center of the charge to where we want the field. And the direction of the field is in the radial direction, outward from a positive charge. If this is a negative charge, the field would be going against the radial direction. So our radial direction, we have a unit vector, a sub r, so we can write the electric field at some point out a distance r from the center of the sphere as the magnitude e sub r in the radial direction. That's assuming we have a positive charge on that sphere. For this derivation, I'm assuming that when we put a charge q on a conducting sphere, that all that charge is going to uniformly distribute itself over the surface of that sphere. So, if we have a conducting sphere and we place a charge q on it, all that charge is going to uniformly distribute itself on the surface. And we're interested in finding the field at some point outside of this sphere. Well, with the charge being uniformly distributed, then by Gauss's law, we know this will be the field at a distance capital R from the center of the sphere out to a point. I indicate that the radial vector from the center of the sphere, which has radius a, out to a point, has position vector capital R. And the a sub r direction, or the unit vector, is directed from the center of the sphere of radius a out to the point where we are interested in finding the electric field. So capital R vector can be written as capital R scalar times the position vector AR, where the scalar R is just the magnitude of the position vector. That's this distance here from the center of the sphere of radius A out to a point in space that we want to know the electric field. And by Gauss's law, if the charge is uniformly distributed around the surface of the sphere, this is the value of the electric field. That's why we need to assume that the charge is uniformly distributed on the surface of the sphere so that we can use this equation for the electric field. I will discuss in a little bit why this isn't exactly true. If we have another sphere, say with minus q on it, with charge uniformly distributed that's way far away from this sphere. This is true if each sphere, say, is isolated in space and we put a charge on it, the charge will uniformly distribute itself on the surface of the sphere. But when we bring the two spheres together, then the field of this sphere induces charge on this sphere, causes some of the charge to migrate, and the same thing with this sphere's effect on this one. For since this charge has a minus q, the positive charge on this sphere is going to be attracted, and it induces, this sphere induces some of this charge to migrate over to this side of the surface. So we have a little bit of more charge on this side of the surface that faces this sphere. And the same thing here. The field of this sphere is going to affect and induce charge migration on this sphere. So the positive charge here will cause some of the negative charge to move and collect on the surface that's facing this sphere. This is called the proximity effect. And I'll be discussing that here a little more into the video. Now, this assumption that we're making that the charge will uniformly distribute itself on the sphere is a very good approximation. It turns out with the proximity effect there's a slight redistribution and it changes the value of the capacitance, the electric field, and hence the capacitance, but it's not a strong effect, and the derivation that we're making is pretty good. But if somebody knows how to determine the mathematical redistribution of the charges due to proximity effect, I'd like to know that. I've been looking at that and I haven't quite got it figured out yet, but if somebody out there knows how to calculate this redistribution of charge as a function of separation distance due to proximity effect, I'd like to know how to do that. Now, using this fact, we know from the symmetry here that the field line on the axial line drawn between the two centers has to be given by this, and we know exactly what the direction is. It will be in the direction or along that radial line. So I'm going to define the positive AR direction as going from the center of the smaller sphere. I'm assuming that B is greater than A. So the radial direction goes from the center of the smaller sphere outward. So the field, the electric field, at some point, little r, out from the center of the smaller sphere, is the sum of the fields contributed by this sphere plus the field contributed by this field, this sphere. This is a linear field problem, and because it's a linear field, superposition applies. So the field at this position is the sum of the contributions of the field from each of the spheres. In this sphere, the smaller sphere, we're assuming it has a positive charge on it. So the field is directed radially out in this direction, and the field from the larger sphere, which has a minus q on it, has a field that goes into it. The field is radially outward directed if you have positive charge, and the field is radially into the center of the sphere if you have a minus charge. This is just Gauss's law, an application of Gauss's law. So given that we know from this geometry we can find EA, well, I can write that the electric field from sphere A is going to be Q over 4 pi epsilon r sub a squared in the a sub ra direction. This is what I would call the a sub r direction, and this is the unit vector going from the center of the sphere A. So I'll just call that the a r sub a direction, and the distance is cap r sub a. That is, going from the center of sphere A out to this point, we have a radial vector r sub a. And I can write that r sub a is just going to be little r in the a r direction. This is how I've chosen my unit vector. That is, in this case, a r sub a is just a sub r. It's just equal to a sub r. Now, the electric field due to sphere B has a minus q on it, so it will be 4 pi epsilon r sub b squared in the a r sub b direction. Well, the a r sub b direction is this direction, so a r sub b, since it's in this direction, it is opposite to a sub r, so I write this as minus a sub r. And I can write that the radial vector r sub b will be this distance. Well, this distance is d less r. That is, along here, this is d minus r. That's what that distance is. So r sub b then will be d minus r in the AR direction with a minus sign, because it's in the minus a sub r direction because it has a minus q on it. Now, the electric field at this point I'll call ET. ET, the total field, is E sub A plus E sub B, the contributions to each sphere. So, combining, I can write now that ET is, we have Q over 4 pi epsilon R sub A squared. Well, R sub A, the magnitude, R sub A is the magnitude of the radial vector, or this will be little r squared, in the a sub r direction. This is E sub A, plus the contribution EB. Well, EB is minus Q over 4 pi epsilon, the radial direction, the magnitude of RB squared. The magnitude of RB is just D minus R. So this is D minus R squared in the AR direction. So, there's our total electric field along the radial line for any position between the two spheres. Just for completeness here, we'll write that R sub A is the magnitude of the vector R sub A, which is R, and R sub B is the magnitude of the radial vector RB, which is D minus R. I need to make a slight correction here. I put the wrong value down for the radial vector. The radial vector for the larger sphere, which has a minus charge on it, is in the minus AR direction. And in case you missed that, I'll show you that here. Is remember, we define the electric field from a sphere of charge as being q over 4 pi epsilon r squared, where r is the distance from the center of the spherical charge to a point in space that I want to find the electric field. And the AR direction, the radial direction, is directed outward from the center of the sphere. Well, for this sphere, the radial direction is outward, but it's in the minus AR direction that I've decided to use for expressing my electric fields. So the ARB is minus AR direction. The ARB is in this direction. It's opposite to the AR direction, and we have a minus Q for the charge. The charge on this sphere is minus Q. So we have here minus Q over 4 pi epsilon, and then this is our cap ARB, or our cap RB. Remember, RB is D minus R. So this is D minus R squared, but my radial vector outward is in the minus AR direction, so I needed to have a minus sign there. So we have a minus minus that will give us a plus. So I can write this field now, the total field. I'm going to factor out a Q over 4 pi epsilon. So this becomes 1 over R squared plus 1 over D minus R squared, and it's in the AR direction. Okay, so that's our total field for any point on the radial line that connects the center of the two spheres. Now, let's look at the definition of voltage. Voltage is defined to be the voltage between 2 points A and B is minus the integral from point B to point A of E dot dl, where E is the electric field and dl is the differential path length on the path that goes between A and B. Now, dl in this case is away from the positive charge, or we can write it as dr in the AR direction. That is my differential vector length. If I integrate along this line, the differential length I'm defining to be in this direction, in the AR direction. This is my differential path length. So that's in the AR direction. Now, B is the initial position on the integration, and A is the final position on the path of integration. We choose a path, and the path I'm choosing is going to be the easiest path in the radial line that connects the two centers, because we know what the electric field is there. So the voltage definition, this path length integral, is assuming that you're going against the field. You're starting at a point B, which is at a lower potential. And you're integrating to a point of a higher potential. Now, the lower potential is over here by the negative charge, and we're going to the positive charge. That means that the electric field, our total electric field, is in that direction. So we integrate against the field. We go from lower potential to higher potential. So we're going from B to A. And what we're going to do is we're integrating from the surface of sphere B to the surface of sphere A. So we're going to integrate along this path. So now I can write my voltage integral, the line integral. I'm going to look at E dot dl. In this case, we're going to go from our surface of B to the surface of A on Et dot dl, which is in this case, it'll be dr in the AR direction. That's our dl. So I will now write the voltage integral. The voltage is going to be, we define it as voltage from B to A, or VA minus VB, the higher potential minus the lower potential. This is VA minus VB, and this is equal to minus the integral of the surface of A to the surface of B to the surface of A of E T dot dr in the AR direction, and our ET, we put in this value for our ET. So I'm going to write that out here. So we're going from the surface of B to the surface of A. Okay, I'm going to write this out now over here. I'm going to move the minus sign over. So I'll have minus V is equal to the integral from the surface of B to the surface of A. We put in for our total electric field, which is 4 pi epsilon times 1 over r squared plus 1 over d minus r squared in the AR direction, and we dot that with dr AR. Just get rid of this stuff here. Now, whenever we have a vector dotted with itself, we just get its magnitude squared. These are unit vectors, so AR dot AR is just equal to unity, or equal to 1. So we can now write this vector integral, this vector line integral, as a scalar integral. We'll get rid of the dot product. Now, also, we need to look at our limits. Well, what we're doing is we are integrating from the surface of B to the surface of A. Well, and we're doing it with respect to our R variable, which goes from the center of sphere A radially outward. So what's the surface of B in terms of that? Well, the surface of B is here. Well, what's R equal to at this point? Well, it's the total distance between the centers, which is D, less the radius of sphere B. So this becomes D minus B on the lower limit, and then to get to the surface of A, sphere A, it's just the radius of A. So we're going to A. So those are our limits. Now I'll rewrite this. So this now becomes what I'm going to do here is I'm going to multiply, bring the q over 4 pi epsilon, this constant over, so I only have to write it once. So I'm going to write this as minus 4 pi epsilon over q times v, which is equal to the integral from d minus b to a of 1 over r squared plus 1 over d minus r squared dr. I can now expand this integral out as the sum of two integrals. So this will be the integral from d minus b to a of dr over r squared plus the integral d minus b to a of dr over d minus r squared. Now the first integral, we just recognize that as being r to the minus 2, and integrating that, we raise it a power, divide by the power, so this becomes minus 1 over r evaluated from d minus b to a, and then we have this integral, but we make a variable substitution. We'll make d minus r is equal to u. So then minus dr is equal to du, taking a differential of both sides. And then when r is d minus b, u is equal to b, putting in d minus b for r here. And then when u is equal to a, or r is equal to a, our u then becomes d minus a. These are our new limits in terms of the u variable. We're going to make the substitution for r by using u. So when r, again, is d minus b, our u becomes b. And when r is equal to a, u is d minus a. And then this integral becomes du minus du over u squared with the new limits, which is when r is d minus b, our lower limit is b, and when r is equal to a, we have d minus a. So we again recognize this as being the same integral as what we just got through evaluating. So we have a minus sign, and then when we integrate this, we get a minus 1 over u evaluated from b to d minus a. And we have a minus minus, so I'll just make that plus. And that's equal to minus 4 pi epsilon v over q. So let's go ahead and put that up here. We have minus 4 pi epsilon over qv. And this, evaluating, we have a minus 1 over a, minus sign out in front. So we evaluate from, pulling out the minus sign. This is, we evaluate from a, which gives us a 1 over a minus the lower limit 1 over d minus b. And then from this integral we have evaluate upper limit 1 over d minus a minus 1 over b. I'm going to move the minus sign through. So we have over here, if I multiply through by minus, we get 4 pi epsilon QV is equal to 1 over A minus 1 over D minus B. And then we have a minus going through here, so 1 over B minus 1 over D minus A. So combining like terms in such a way to reveal a little more information here. I'm going to write this as I'm going to collect, put it as 1 over A plus 1 over B minus 1 over D minus A plus 1 over D minus B. So now we have the expression for our potential difference between the two spheres. This becomes Q over 4 pi epsilon times 1 over A plus 1 over B minus 1 over D minus A plus 1 over D minus B. Now, remember our capacitance is the ratio of Q to V. So to get Q, C equals Q over V, we bring the V down and bring this over to the other side. So this now becomes 4 pi epsilon over 1 over A plus 1 over B minus 1 over D minus A plus 1 over D minus B. So there's our capacitance. Now, I'm going to multiply numerator and denominator through by A. So I get 4 pi epsilon A, and this becomes 1 plus A over B minus A over D minus A plus A over D minus B. And this is under the condition that B is greater than A. Right here, that we made our assumption. So there's the value for capacitance. Now let's note, if the spheres are of the same size, if B is equal to A, let's say, then our capacitance, we can write it as 4 pi epsilon A. B is equal to A, so that's 2 minus, if B is equal to A, then these are the same, so this becomes 2A over D minus A. And we can factor all to 2, so this becomes 2 pi epsilon A over 1 minus A over D minus A. A simplified expression. Now, if we can make this even a little easier, let M equal A over D. That is the ratio of the radius of the sphere to their separation. And if I do that, then my capacitance becomes 2 pi epsilon A over 1 minus M over 1 minus M. Now, let's look at this a little further. So there's our expression for the capacitance between two spheres of unequal radii. The derivation of this capacitance is assuming that all the charge on both of these spheres is uniformly distributed around the surface of the sphere, so that we could use the expression for the electric field for a spherical charge with uniform charge distribution on the surface. Now, in general, this isn't true. There's a thing called proximity effect, that when you take, say if I put a charge Q on this sphere and minus Q on this sphere and had them separated by a very, very large distance, then the assumption that the charge is uniformly distributed on each surface is a good assumption. And for all practical purposes, the charge will be uniformly distributed over the surface of the sphere when the separation distance d is very, very, very much larger than the size of either of the two spheres. Now, as you bring them together, you get induced charges due to the field of one sphere acting on the other sphere. And as they come in closer together, what happens is the positive charge on this sphere moves negative charge on this sphere over more to this side of the sphere than on that side. And likewise, the field of this sphere, this being minus Q, moves the positive charge on this sphere. It's induced, it pulls more of the positive charge over to this side. This is called the proximity effect. Now, what does this do? Well, this complicates the expression for getting the electric field, because we can no longer assume that the fields are uniformly distributed. Well, how much does that change the field? Well, there's no easy way to determine that. The induced charges migrate to the sides of the spheres that are facing one another. Now, but what we can do is we can argue that this value of capacitance places an upper bound on the actual capacitance between the two spheres. And we can argue it in this manner. Remember that voltage is minus the integral of E dot dl. And we know that the electric field is the electric field density divided by epsilon, and by Gauss's law we know that the electric field density is equal to the surface charge, and the D field is everywhere normal to the surface. That's a boundary condition placed by Gauss's law and Maxwell's equations. Now, D field begins and ends on surface charge, or on charge. That's what that equation is telling us. So, if we have a slightly more dense concentration of charge on the surface of the sphere that's facing the other sphere, rho sub s is larger than it is when the charge is uniformly distributed. So, I can say that the D, when you have proximity effect, along this radial line in this area is going to be greater than the D when we had uniformly distributed charge. So the D fields are going to be slightly larger at the surface of the sphere as they're brought together than they were when we have a uniformly distributed charge. So this implies then that the E field, due to proximity effect, is going to be greater than the E field when you had a uniformly distributed charge on the surface. Well, if that's the case, then the voltage between the two spheres when you have a proximity effect is going to be greater than when it was evenly. The voltage is E dot dl. So we can say that the voltage between the two will just basically be minus E times when we integrate from one surface to the other, which is proportional to the separation distance between them. So the distance between them, between the surfaces, will just be D minus B minus A. And once we bring the spheres to the same separation distance, D, this doesn't change. So the only thing that's changing is the E field. So I'll call this, say, a D prime. So this becomes minus E D primed. That's our voltage. So we then have that the E field due to the proximity effect times the separation distance is greater than the E field when we assume the charge is uniform. So this tells us then that the voltage, when you have a proximity effect, is greater than the voltage when you have the uniform charge. That being the case, since capacitance is a ratio of charge divided by voltage, the voltage when you have a proximity effect is greater than the voltage when you assume uniform charge distribution. So the capacitance, or in this case 1 over, let's write here, 1 over voltage when you have a uniformly distributed charge is going to be greater than 1 over the voltage with proximity. If we multiply through by Q, then we see that the capacitance when you have a uniform charge distribution is going to be greater than the capacitance when you have proximity effects. So this places an upper bound on the capacitance, which is good to know. So we know that the capacitance between the spheres is always going to be bounded by this value. So it gives us an approximation to the real world case, and it turns out that the capacitance, when you bring the charges in towards one another, it doesn't change that much from the theoretical value, assuming a uniform charge distribution.